Hello, welcome to our next set of stats notes. We are on section 9.3. We're in the last section for chapter 9 for us. Next section will be moving on to chapter 10. So we're doing one more set of two population situations. So we're going to be dealing with doing hypothesis tests and confidence intervals. We have two different samples. But the big difference with this section, and what makes this section unique, is that this time the samples are going to be paired. These are going to be matched pairs. So for some reason, there's going to be some reason why the two sets of data we're working with have direct ties. So you might be dealing with data where one set is husbands, the other set is wives. You might be dealing with data where it's siblings, and so the older sibling, younger sibling. But there's going to be some reason why these things will be tied together, will be paired. So we're going to use paired samples. So it consists of a member of one population that has a corresponding member in the other population. So that's going to be what makes this one special. Now, when we choose simple random paired samples, you should have every possible pair should be equally likely. Typically what that's going to look like is like if you were doing a study where you're looking at the mean income for bigs and littles in the Big Brother, Big Sister program, you would like randomly choose bigs that you would look at and then study their income, and then just study their corresponding little that they are tied together with. Because that might be one way where you could get a simple random sample. So I'm not going to read too much about that because they're just going to give us the data as far as the homework and solving problems for this class is concerned. But in real life, that's one thing you have to think about is how do you get pairs and making sure everything has equal chances and all that. Okay, so when you're comparing two populations with paired samples, what we'll do is instead of working with both sets of data most of the time, we'll actually look at the paired difference variable. So this is the difference between the values of a pair. So instead of looking at both numbers, we'll just subtract the two and find their difference. In fact, it's true that the mean of the paired difference variable is equal to the difference of the population means. So it is a rule that says, if you look at the two means separately and subtract them, you get the same average as if you would take just the average of all the differences. So that's what this rule says. So instead of trying to deal with the two numbers separately, we're just going to look at the mean of the differences. We're going to take the data and we're going to subtract matching values, and we're just going to look at these differences. As always, when we're doing hypothesis tests, we do need a test statistic, and this would be the calculation for a test statistic, where this D bar, this could be the average of the differences for your sample, and this mean sub D, this is going to be the average of the differences for the entire population, the number we're trying to usually estimate. Sample D is going to be, the sample standard deviation for the differences. So that's what these guys are, D and SD. Sample mean and sample standard deviation. Not really going to see a lot of work with these because we'll depend on technology and it's going to save us a lot of time. One nice thing is that since we're matching up the pairs and combining them, we get to go back to simple degrees of freedom where you just take the sample size and subtract 1. With these, because you're always working matched pairs, the samples for the two groups will always be the same size because you always pick the same number from both sets. Okay, so do a hypothesis test. With working these, we're going to typically be given the actual data. And that's a big difference because so far we haven't been really giving the data. They've been giving us the statistics, the mean, the standard deviation, that kind of stuff. In this case, we're going to be given the data values. And so to do this, we're actually going to have the data and we're going to calculate from there. We're not going to use the stats as much. So what we'll do is we'll compute the differences from the data they give us, and then we'll do a hypothesis test on the set of differences. So instead of working with the two sets of data they give us directly, we're going to take them to find the differences and then work on that set of data. As we've seen in the last couple sections, the null hypothesis will be that the population means are equal. If your two population means are the same, then their differences, the difference should equal 0, right? If the two populations match, and then the set of differences where you subtract them, then that should equal 0 because the differences should be 0 if they match. So we'll actually be working with a situation where we're going to be looking at the differences being, their average being 0. So the null hypothesis will be the set of differences, the average is 0. So mu sub D, the mean of the differences, equals 0. That's what that tells us. Okay. we'll get our test statistics, sorry, and then use either the p-value or critical value. We'll typically use p-value because, again, technology will just give us a better way to use the p-value. So you could do it with the critical value, but we're not really going to worry about that. We're just going to use the p-value from technology. Okay, so let's see it in practice, because honestly with this stuff, I think that's the big thing, is just seeing how you do it in practice. So they give us, use the data from the tables below. So here's our data. Perform a hypothesis test at the 5% significance level. So that's going to be our alpha, our significance level. The null hypothesis is that the means are equal, or that the mean of the differences is 0. And the alternative hypothesis is that they're not the same. So the alternative case, in this case, would be that the mean of the differences is not equal to 0. If they had less than or greater than here, you could say if it's bigger or less than 0. But that would be kind of the idea. This is the statements, but we're going to think about the differences. So what we're going to do is we're going to take this chart, and we're going to expand it by a row. We're going to have the differences. So we're going to find the differences of all these. Now you could just sit here and subtract these, and that would give this number. But there's actually a little slick trick way to do this. I'm going to show you real quick how to do this slick way. I like this way because it kind of saves you from maybe making as many mistakes. So what I do is I go to Stats and Edit, and actually just enter this data in my list. So by entering the data, I can see all the numbers and make sure I have them all typed in there. Make sure I don't miss any values. I'm going to do that. I'm going to type all these numbers in here. List 1. Okay, 7, and then 18, and then 11. And then I'm going to do the same thing, type in the next set here. So I have 8, 11, 6, 16, 3, 19, and 8. And they should be the same length. They'll always give you equally like that list, for length here. And then what you can do is you can actually go in here and you can actually get this third list by subtracting these two lists. So I'm going to type second list 1 minus second list 2. And hit enter. And it just gives you the distances for you, the differences. So instead of having to do that, I can just make this list 1, this list 2, and this one is list 1 minus list 2. And that's the method for doing that. So I went to the very top where list 3 was, and typed in second list 1 minus second list 2, and hit enter, and that's how it filled it in for me. So that way you're making sure everything's matched up properly, and if you type it in here first, you can really make sure that you got it typed in correctly. And it just kind of saves you making no mistakes, because if you sit there and type in all these subtraction problems, it's easy to make one mistake that gets the whole thing wrong on you. Okay, so I got 1, 4, 2, 5, 4, -1, and 3. And that's my list of differences. So now when I go to do these, I'm going to use this list of differences. I'm not actually going to use these two lists anymore because I got the distant differences to work with. I am going to do just a regular old t-test because I'm only working with one set of data. So that's the nice thing. Because I'm just working with this one set of data, I can just do a t-test. This is a problem with means, not proportions. So that's why we are going to use t-test and not z-test. Stats, test, t-test. Now this time, instead of doing input and doing the stats, I'm going to do the data because we actually have the data values. I'm going to do data. Oops, I hit this wrong button. Let's clear that out. Stat, test, t-test. I'm going to go to data and hit enter. So our input, data. The mean sub 0, that's going to be 0. So we already mentioned up here that we want the average of these differences to be 0 if the two populations are the same. So we're going to make that 0. So mean sub 0 is 0. List we're going to use, we're actually going to use list 3 because that's where our differences are. So I'm going to hit second list 3. So I'm just pressing this button down here because that's your list 3 button after you hit second. So the list is list 3. Frequency you can just leave as a 1, don't have to change that. In this case, we're doing a not equal to, so we're going to hit the not equal to for that. So the mean is not equal to mu sub 0. And then calculate. And this will give us our data from that. So from this, we get the t-score, 3.286. We get the p-value, 0.016669, around that. This gives us the sample mean, so that's going to be the mean of this sample data right here. So you can have that. We don't really need it, but it does give you that. And it gives you the sample standard deviation. So the standard deviation for this would be 2.07. So that would actually be that standard deviation of the differences and the mean of the differences. You could put that as D bar, I guess. So from that, now we're ready to actually check it, do the hypothesis test. As usual, since they gave us the p-value, so doing this t-test gave us the p-value, we'll just compare the p-value with the significance level, the alpha. So the p-value is 0.01669. The significance level is 5% or 0.05. Remember to always turn that into a decimal. And you can see that this one is definitely smaller than 0.05. This is only 1%, that's 5%. So again, if the p-value is small enough, then we reject the null. So were they equal? No. There was actually an average difference that was 2.5. So the differences don't average out to 0, actually average out to a number bigger than 0. So there's actually a significant difference between these two. These two sets are different. You can kind of see that here where most of these come out positive. It kind of shows that this set is a little bit bigger than this set. So that's what we ended up seeing. So we rejected the null because we showed that the p-value is small, small enough that we could reject. The sets are not equal. So the mu sub d, the average of the differences is not 0. That's what we're going to support because we were able to reject the null. And so that's what it's going to be for set problems in this section. You're just going to be finding that differences. You're going to find the differences and just run a t-test on the differences. We're looking for 0, so that's why this is going to be 0, because we're looking for the differences to be nothing, because if they are nothing, then the sets are equal. But if they're not nothing, if they're more than nothing, like this one, 2.57 was the average, then you reject them and only say, nope, they weren't equal. These two sets are different. They are different. Okay, that's your hypothesis test for this section. So it's just running a t-test, but you do have to use the data this time, and you have to use those data results we got. Now let's go ahead and do a confidence interval, but it's going to be very similar. We're going to use the same set of data here, so we don't change things too much. So as we've seen before, we can do the hypothesis test. Then we can also calculate the confidence interval, so that's also doable. We use the differences as the point estimate. So the difference would be your point estimate if you're constructing this by hand without a calculator. And the margin of error would be this formula. So that's the margin of error. Again, we're not really going to use these formulas because we'll let the calculator do it for us. Constructing the confidence interval by hand works the same as usual. Adding and subtracting the margin of error from the point estimate, just like you always would. However, we saw with the hypothesis test, it's easier just to use technology. So that's what we're going to do. Don't forget, if 0 is not in the confidence interval, then we have sufficient evidence to reject the null. So if 0 does not fall in the confidence interval, we have sufficient evidence to reject the null hypothesis, meaning the populations aren't equal. So we're going to do this with the same two populations. We're doing a 95% confidence interval. So that's our confidence interval. And we are going to just do a t-interval. So we're doing a t-interval. But again, we're not going to do it with the two sets of data we're given. We're going to do it with the set of the differences. So again, we're going to have to take these two sets and we're going to subtract those and find that set of differences. I've already done that, so we don't have to redo it. But if you want to do it, you can put that in list 1, list 2, and do all that. And we get 1, 4, 2, 5, 4, -1, 3. And that was our set of differences. That's our list 3. This is list 1 minus list 2. Give us list 3. And so we'll use that and do our t-intervals. We're going to go stat, tests, scroll down to t-interval. There it is, t-interval. Again, we're doing means. That's why we're doing t-scores. T's are for means. We only use the z-scores for proportions. And if you're doing proportions, you're going to be using the proportion option anyways. Okay, t-interval, we're using the data again. So we definitely want our input to be data. The list, be list 3. Frequency leave that's 1. This is a 95% is what I want, so the C level would be 0.95. We'll just calculate. So the confidence interval we get is 0.6568 to 4.486. And you can see here that this confidence interval does not contain 0, right? These are both positive. So this would actually be a reason to reject the hypothesis, the null hypothesis, because this does not contain 0. Does not contain 0. Reject the null. This one is really straightforward, and that's pretty much all you're going to be doing in this section. Is you're going to be doing hypothesis tests, confidence intervals. Yes, you have to work with a set of differences, not just with the data themselves, but that makes it easier because then we can just use regular t intervals and regular t tests, right? So we're not going to have to do anything more complicated than that because we're working with the difference data that we got by combining the two sets. Again, the reason you get to do this, the way you know you're doing these type of problems, is they'll give you the data and it will be matched pairs. When the data is all matched up like this, that's when you can just subtract and find the differences. In previous sections, in 9.1, 9.2, the data wasn't matched up. There was no natural link between the data, so it wouldn't make sense to subtract. In fact, sometimes you'd have different sets of sample data where they'd be different sizes, so you couldn't even subtract everything. So this section, big difference is because everything's naturally paired like this, it makes sense to work with the differences instead. Okay, so that's it for chapter 9. We're done with working with all these two sets of data. We're going to go on. We are still going to actually work with two different aspects of data, but we're going to be looking at a very different way in chapter 10. So we'll get to chapter 10. We'll talk about regression and all that stuff. And that's where I'll see you on the next time.